So, in the last lecture we explained how the ultimate limit state in terms of design mechanism, how the partial safety factors can be connected to a reliability approach where R and S are seen as variables in reliability approach, random variables, whereas in design they are not directly seen as random variable, but the effect of their variations or uncertainties are accounted in terms of using or substituting for the partial safety factors of load effects and the resistance, that is gamma Si and gamma R. So, one should be able to estimate these values using reliability theory. Therefore, one can be sure deterministically that what would be the probability of failure if you are using a specific characteristic value of the load and that of the strength and are using specific safety factors for load and resistance respectively. Now, let us say we want to look for short term reliability. To make it easy, let us consider this for a single load effect. First of all, why do we call this a short term reliability? Let us understand or let us assume that within a period of time, let us say t, the variation in resistance is not valid. What does it mean is R does not vary much, not significant, which can be true because using the same material for a period of let us say structural life of 15 years and the material has got a very high quality control in terms of its manufacturing processes. Therefore, the variation in terms of its yield strength, in terms of modulus of elasticity etc., can be ignored because the variation practically will not be there, right, though the variation will be there because of the strength deterioration, degradation etc., but let us say assume that for a specific short term period that t we will fix maybe 1 year, maybe 6 months, maybe 10 years. For a specific period, if R does not vary, the variation is only on the load effects yes, then one can consider the distribution of individual maxima of the load effect, which could be the largest value within the period t. You can consider the largest value, what we call maximum. In that case, reliability problem can be framed using what we call extreme value statistics. So, the failure probability in the short period of time that is 0 and t is given by Pf which is now meant for a specific time, let us say Pf of t, because t is a period where I am looking at. one can say however the time period of t is very large, still I can call this a short term, because considering the design period of 100 years, considering the service life of 25 years, any value you take can be considered as a short period or short term. Okay. So, probability of g of, that is the failure function, which can be a function of r and s max, or let us say s varying from 0 less than t less than t, t is between 0 and t only, and we can now look for maximum of s amongst q of t. Which can be less than or equal to 0. Let us take q of t, where t is a variable here. This can be also rewritten as the failure function, that is probability of g of r comma s max. I am saying this is an x max value within a period t, which can be less than or equal to 0. I will call C question number 1. So, what I am trying to say here is, if load is not considered, sorry, if the resistance is not considered to be varied within a specific time t, consider only the maxima of the load effect and form a failure function and find the failure. Okay? That is what we call as short term reliability, where g is the limit state function, it is written as, I think you can write it legibly here, g of some function, some parameter. In my case r and s are the parameters. R is the resistance, and S is the load effect, resulting from the process Q of t. That is the load process. I am looking for the maximum value in the given load process within a period 0 to capital T. I can also call that as S max. Okay? That is what the language of this failure function means. Alternatively, there is another approach for this. There is a second approach for this. Alternatively, the failure function can also be expressed by upcrossing method. Let us see what is this upcrossing method. In this method, upcrossing rate is established So, in case of reliability, the main focus is to estimate T suffix f, where T suffix f is the time of first failure. So, for a simple problem we already know that is the safety margin m of t, which is a function of r comma s of t. I think you will agree that why I am not writing r as a function of t, we already said that r is not varying, okay, which can be simply r minus, that is my margin of safety, is it right? Equation number 2, r minus s of t, where Tf is the first time when m of t is 0, okay. So, failure. So, probability of failure is now addressed in a different form as given below. So, instead of looking at r exceeding s or s exceeding r, I am now going to look at what is the time when m of t becoming 0 and what is the time at which this occurs for the first time. Okay. I am just rewriting the problem into a failure function and writing this probability of failure in terms of estimating Tf, okay, that is called upcrossing rate approach. So, it is equivalent to the probability that Tf is less than t. It means within your short term time t there is going to be a failure, okay, that is what probability of failure is. If within your capital time t, if the failure does not occur, the probability of failure is 0, 100% reliable, is it not? So, I am looking at the problem in a different perspective, saying that what is the probability that Tf less than t can occur. What is Tf? Tf is the time at which the first failure has occurred. Is it very clear, right? So, I am looking for a short term reliability where I am trying to find out the upcrossing rate of this function, which is r minus s or margin of safety, and what is the first time at which this is going to occur, and what is the probability that this will occur within t. That is my problem now, okay. So, I can write the probability of failure now as t, because again it is a function of time, which is 1 minus probability of Tf greater than t, is that correct? Because Tf less than t is a failure, which can be said as 1 minus probability of n of t set to 0 given m is the margin of safety, m of 0 greater than 0. Multiplied by probability of m of 0 greater than 0. I call this equation number 3, I call this as 3a and 3b. There is a multiplication here, okay. I do not have a space, I have written like this. Now, the question is, what do you understand by n of t, where n of t is the number of upcrossings within the interval 0 to t. okay, since I am saying n of 0 to t, that is the number of upcrossings from the safe domain to failure domain. I mean, how many times your margin of safety is not satisfied. What is margin of safety? R minus S of t. If R minus S of t is set to 0, it is on the border, right. So, you must first know the condition, what is the margin of safety. Given that condition, how many times this has occurred, that will be a probability of failure. Okay. Now, in this case m0 greater than 0 signifies m0 greater than 0 signifies that the safety margin. What do you mean by m greater than 0? R is greater than S. Is it safe or unsafe? Safe. So, m greater than 0 indicates safety margin, where m of t is R minus S of t is in the safe domain. At 0 time. That is why I have used 0 here. Okay. That is the reason why I have used 0 here. At 0th time this will be applicable, okay, it is safe. Now, from 0 to capital T, what is the probability or how many number of times this has been violated? That is my probability of failure. Okay. Now, in this example or in this derivation, calculating Pf of t is a complex task. It is a complex task. Therefore, an approximation is made. An approximation of n of t assumed as Poisson's process is adopted to compute P of t. What does it mean? When I say n of t is Poisson process, it means that for n of t being a Poisson's process, it means that upcrossing level of R and S of t are independent. They happen independently. With the maximum rate of Vs plus R is equal to Vm minus 0. So, whereas Vs plus R is the maximum rate of upcrossing, okay, it is indicated as Vs plus R, and this happens per unit time. That is why it is called as rate of upcrossing. Okay. So, now probability of n of t exceeding 0 upcrossing, or let us say equal to 0, because upcrossing means it is 0. You have a signal, for example, you want to find how many times signal has crossed 0, you look for only the forward slopes, okay, look for only the forward slopes and so on, how many times it has crossed in a given t. So, for identifying the forward slopes you must look at this value of equal to 0, okay. So, probability of n of t set to 0 can be now given by, now using the maximum rate of upcrossing, I am using VSR plus now, VSR, this is R, of t to the power 0 divided by 0 factorial, that is a general expression. E to the power of minus VSR of t, which can be simply E R of t. Okay. Can call this equation number 4a and 4b. Now, the probability of m0 greater than 0, that is safety margin at 0th time, is nothing but 1 minus probability of failure at 0, is it not? Which means that there is no failure at t equals 0, agreed? Hence, probability of failure at 0 can be taken as 0 because there is no failure at 0. Then probability of failure at t can be approximately given by 1 minus, I am using this, e to the power of minus V s plus r of t, which can be approximately V s r of t, this is approximate, which can also be said as, we already said this here, V m minus of 0 of t, called C equation number 5. Now, as a special case, if S of t is a Gaussian process, then V of s plus r can be said as V of 0 exponential r minus mu s the whole square by 2 sigma s square. It is an exponential value. I call this equation number 6. Where V0 plus this value is as same as Vs plus of 0. So, this is a second approach by which I can find out the probability of failure using upcrossing rate, which is Vs plus R0 for a short term reliability where R is not varying significantly, whereas load effect S is varying significantly within a period of 0 to capital T, and I am looking for Tf, which is the first time at which this failure has occurred. Okay, and n number of times this failure has occurred or margin of safety is violated, thinking that at 0 is absolutely safe. Okay, at 0 it is absolutely safe. Clear? Okay. Now, the given values of R, let us say instead of R we should say generally the given values of random variables x, that is x1, x2, etc., which represent the uncertainties the conditional probability of failure is given by the down crossing of m of t. So far we have been seeing the up crossing of m of t and x for t greater than 0. So this can be given by the probability of failure of x, which is a random variable, varies from x1, x2, x3. Okay, please make a correction here, the random variable is a transpose of this, it is a vector, can be given by the probability of minimum value of, earlier we looked at the maximum value, okay, if it is S effect. Now I am looking for the margin of safety, so I should look for the minimum effect, okay. Marginally it is unsafe or safe, margin of safety. So minimum value of 0 less than t less than capital T, same argument, m of t given x, for a given set of x I am looking at t less than equal to 0. What does it mean less than equal to 0? R is less than S, so it is unsafe, okay. That is a failure, which can be said as 1 minus exponential of minus Vm minus of 0. I am looking the down crossing, therefore I am putting minus here, okay. Down crossing means negative, which is happening arguments are 0 and x for given t. I can call this as equation number, what is the number? 7, 0 of t. Let me check this expression. Where Pm minus of 0 x is a 0 down crossing rate of margin of safety which depends on the vector x, and the vector s is a function of r and s. Okay, margin of safety is nothing but r minus s. Now, the total probability of failure considering the uncertainties in x for the given conditional probability can be said as probability of failure Okay, now let us make it as unconditional for the given unconditional, this is unconditional. Is given by probability of failure which can be integral over the domain x, that is the random variable set, P of xx f of xx dx. This is capital X. Equation number 8, where the integral represents expected value of the variable x or the probability of failure, because it is not the variable, it is the probability of failure of x hence the average value is given by P of xi, where xi are generated by Monte Carlo simulation. Therefore, we can say P of f in this case is going to be an average of n values of equation number 9. Of course, this is an approximate value, okay, cannot be accurate. So, this is the short term effect of reliability for a specific time period t, where R is not varying significantly compared to that of load effect S. Now, let us look at the long term variability. Not variability, actually it is long term reliability. All the load effects. Long term reliability, we are talking about the single load here. Earlier also we discussed about the single load only. So, now let us say for a non-stationary process, which is let us say m t of x, some process which could be for a long term period. Failure probability is given by that is my domain. Vm minus Vm is the function here what I am arguing, therefore, it is the down crossing rate and the variables are 0, t and x for a time period dt, that is a variable. So, I can call this as equation number 10, where Vm minus of 0 t in x is the mean down crossing rate of margin of safety which of course depends on the C state which C state that changes with time. Why I am saying only C state? Already we are saying that the variation in R is not significant with that of S. Variation is included here because I am not binding this for a specific value of t, I am taking any time t. Okay. If you look at the previous expressions, it was maximum or minimum of the failure function between 0 small t and capital T. So, we are looking only in interval of 0 to t, but here it is an open domain any time t, right. But even in the time t, we are saying the process is non-stationary, which is a margin of safety process, which is having actors as R and S, but the variation in R is not significant compared to that of S, because S is varying significantly because of the C state variation with time. Okay. Suppose if you know for a given C states, suppose for a given C state I can acquire the following details. For a given C state, if the following are acquired. What are they? Which we call them as captured values. What are they? HS, significant wave height, TP, spectral wave period, UC, current velocity, UW, mean wind speed, and also the predominant direction of wave, wind and current. If I am able to collect them or capture them and put these values in a subset called W, capital W, then with the prerequisite of ergodicity assumption, ergodicity. What is an ergodic process? I want you to look back in the standard statistics and understand. Otherwise, they may be available in some other parallel coursework given in NPTEL, in some other literature. In fact, I can quote one of the courses what I did on dynamics. We discussed about the random process in dynamics, where we discussed about ergodicity, stationarity, everything. Please look at that, you will understand what we talk about here. So, we have a captured set of values, and we also say there is a prerequisite that these values are ergodic. That is an assumption. Then W can be written as W of t and probability of failure of the variable x can be now said as 1 minus exponential of minus t for a domain of W, because my W is a captured value now. Okay. Instead of saying 0 to t, I have captured these values for a specific period, okay, and they are ergodic in nature, right. Therefore, I am rewriting this expression 10 in a different form, Vm minus of 0 Tx, okay, instead of t I should say W, because that is my argument now here. F of WW dW, is that clear? I can call this equation number 11. Now, my domain is now transferred to a captured value of W, where I know all these variable parameters which are responsible for my high level of uncertainty in S, where again Vm minus of 0 Wx denotes mean 0 down crossing rate Why down crossing? I am using minus here. Up crossing means I have to use plus. For down crossing rate, okay, rate for m for the C state W, it is not for T. Okay. I should say very specifically C state W equals W, because W are the set of captured values. Okay. Now f of WW, the one which is shown here, is the probability density function of this W. Therefore, the full long term reliability or I should say long term failure probability, one and the same, long term failure probability accounting for both environmental uncertainties. How can you say it is accounted for environmental uncertainties? Because W is a captured value which I have for specific variations including the directions, and their probability density function also I have. Okay. So, it is accounting for environmental uncertainties and variability in the parameters. Which will be given by probability of integral over domain x, probability of x, which is f of x dx, equation number 12. So, in this lecture we have understood what is called short term reliability and what is called long term reliability. In short term reliability there are two approaches we discussed. The famous and common approach is upcrossing rate of the margin of safety, where we have arrived the closed form solution for a single load effect of S. For a long term effect we have used a different methodology of approach, saying that the process is non-stationary. Instead of finding out Tf, which is the first time at which the margin of safety is violated, I am looking for a domain now where T is now transferred to a captured domain of W, small w, where I know all these parameters captured for a given C state. Now, I account for this variability and the parametric variation for a given C state. I am not saying for a given T, I have transformed the T domain to a captured value domain W. Okay. That is how we have said my variation is on the domain W. Okay. So, the expressions I think 8, equation 8 and 12 will give you the probability of failure for a short term reliability and a long term reliability respectively in this discussion. Okay. Now, the question comes, having understood the different levels of uncertainties, having understood its short term and long term effect, having understood the connectivity between reliability and ultimate limit states, which we have seen in the last lecture, what are the different levels of reliabilities, what are the factors affecting each level of reliability, we must discuss this. Once we understand this, we will take it forward and understand what do we mean by methods of reliability, like FO as a method, AOF as a method, etc. There we will end the discussion on this module on reliability of marine structures. Any questions here? You go through this and try to understand. The references is for this specific discussion is in Arvind Nace and Torger Moon, Advanced Marine Structures, where we have given the reference in the NPTEL. Please look at this and study them. Otherwise, you can refer to any standard book on structural reliability, they are discussed. It is a general problem formulation, only certain aspects like this will be particular to marine structures. So, this can be followed easily. Okay? Thank you very much.